My name is Luigi Manca, and today I will want to share with you one of the projects that we did last year and related to how the simulation could play a key role in understanding the benefits of Industry 4.0 initiatives. So, but before starting, just let me spend a few words about us and the company that I represent. So, as John perfectly said in a best Italian, where's John? Engineering Informatica is one big player of system integrator in Italy. Ferdynamics until last year was a limited company that this year has been acquired and merged by incorporation into engineering. Engineering provides a system integration project and is the fifth on the Italian market and the first with a full Italian equity on it. It has different branches abroad. These are some numbers. These figures are related to 2016. Last year in 2017, we reached 1 billion turnover with more than 10,000 people in the company. So the company is quite big in respect of our small team that was in Ferdynamics. Ferdynamics now just remain as a consulting unit inside engineering. So we maintain our distinctive aspect of providing decision-making projects by using modeling and simulation as a key and distinctive factor. So if I have to talk about drivers, maybe the real drivers of my team is more concentrate on solving business issues, solving business problems, while engineering driver is most related to provide to the customer the best technology, the best solution for solving, I can say, exploiting the problem that we solve. Some of the customer, these are the customer of Ferdynamics, not the customer of engineering that are many more. All these customers that I selected here are just I wrote here because we did some simulation project for them, like with a very quick overview. Just for GlaxoSmithKline, we provide a different supply chain project on understanding how the supply chain of vaccine could be resilient to different possible factors and events that could happen. For Pfizer, we provide clinical research and discovery project. For RFI, that is the owner of railroad infrastructure in Italy, we provided risk management asset for the railroad. For Trenitalia, we did marketing project. For Prismian sales forecast. For Bank of Italy, Chiesi Pharmaceutical, and Monte Carlo, we did a resource planning project. And for TIPER, that is the public transport in one big region of Italy, we provide evaluation of asset evaluation. So all these customers were with many different industry, many different problems, but one common thing that had together that we solved all their issue by providing a decision support tool done with the simulation techniques and done with AnyLogic, because internally we just use AnyLogic since we are also the distributor for the Italian market. So the customer. We are talking today about CNH Industrial. CNH Industrial is a global leader, global player in the world about capital goods. So they provide more than 12 brands. I think I hope also in the US, the most known is in Italy for sure. In Europe is Iveco. Iveco provides trucks, buses, or light professional vehicles that are the one that we studied. As you see, numbers are huge and incredible. And CNH Industrial belong to the same holding that of FCA and Ferrari. So just a little introduction to the background. So I talked at the beginning of Industry 4.0. Industry 4.0 is a trending topic. Everybody needs to have at least one or two slides with Industry 4.0 in your presentation, otherwise you're out of the market. And so they are all what about the new industrial revolution? So in all the companies today are trying to understand how new technologies like IoT, artificial intelligence that yesterday Lily talked about, cloud computing could help in improving the performance of production, and how to enable the transition from an actual factory to a smart factory. So, and in this sense, also CNH want to understand, and so this is why it asks us a prototype to identify possible new Industry 4.0 solution on maintenance. And to do that, what we provided was a simulation model in which we try to replicate as a sort of digital twin of the process, not of the product. This is the difference. To provide a digital twin to test in silico different maintenance policies of a production line in order to understand the possible return on investment on advanced maintenance techniques, maintenance policies. So we modeled this line. We modeled different policies like scheduled maintenance, so periodic maintenance that you can. So you have to change the component every certain period. Condition-based maintenance, where you're now trying to already get the benefits from IoT because you get the signal from the machine, you get the raw signal, and you put a threshold. If the component if this threshold is being overpassed, you have to change the component as soon as possible because it's going to fail. And then predictive maintenance that combine the benefits of the two above. So combine the benefit of periodic maintenance because you can schedule in advance when to change the component, and take also the advantages of condition-based because this schedule is related to the actual the actual health status of the component itself. For this first pilot, we just focus, as I said, on a single line to produce the welding body, so the chassis of the Iveco daily vans, so of some vans, and we just focus on one of the most critical components that were the welding guns, so the big robot that weld all the chassis on the stations. Why maintenance? So maintenance is one of the pillars in Industry 4.0, and it's also a pillar in world-class manufacturing. So CNH, like the all FCA brands, is under WHM, the world-class manufacturing program, and is developed this program in order to improve their performance. So world-class manufacturing is a program based on TPM, so total productive maintenance, and with the objective of zero defect, zero wastes, zero losses over your in your production. So the main driver of this is the cost deployment. So you have to improve, so the continuous improvement has to be done in relation to the real impact that a single component has on the losses. On a periodic period, periodic audits are put in place to evaluate the level of world manufacturing implementation in each of the plants of CNH. And CNH had only one gold reward at the time, and the plant that we analyzed, where we put in place our project, was very close to get the second gold. So they were really they took really care attention in understanding possible new technology in order also to get this reward. Another important stuff, second but not for importance, is that when you talk about maintenance, especially in the automotive industry, and CNH is not exactly in automotive because we are talking about vans, and so the takt time is a little bit different, but anyway, is quite close. So downtime costs are really huge. So the total sum, this is a research of 2006. So the survey of 2006, sorry. The total amount of a downtime cost per minute, so the sum of hidden cost and visible cost of a downtime per minute is more than $22,000. So in this case, if you think that a factory is working on 2 or 3 shifts per day, on more than 250 days per year, you can say that a very small percentage improvement in reduce the downtime could save a lot of money. So just to go deeper into the line that we model, this is a picture of a similar line. So here we have the vans, that we have a conveyor in the middle, then we have different stations. The vans stop in each one of these stations, and all the robots work together in order to weld the chassis. In our line, was the line of the called Mascherone line, as 10 stations. We just focused our attention on we modeled the entire line, but for the pilot, we just focused our attention on the orange block. The orange block are where the robots stay. So each block is described with different robots that act to do the work done. And in particular, we took our attention on one component, we took the signal of one component that is related to the shunt of this robot. So these are the shunt where the electrode, between the two electrodes, you have the two pieces of metals that when the shunt close have been welded because of the electricity that pass, and the electricity pass through this lamellar pack that is a flexible conductor and is needed to be flexible because the opening and closing of the shunt. But this movement break the component. So it has been composed by different layers of an alloy of copper. So by the usage, this layer one by one are broken. So changing the resistance and changing the conductivity of the component itself. Sometimes it happens then when the layers are very few, these explode, melting into the shunt. So the changing operation that could take in a normal condition about a few minutes can take hours because all the lamellar pack is melt on the shunt. So you can understand that monitoring this kind of component could be critical for the downtime reduction. Just go through. I think the order is not correct, but anyway. So we provide an agent-based modeling. Again, we are working with AnyLogic since the 2010 close, so we are close to 10 years working, and we think it's still the cutting-edge technology for simulation because it is the only one that provides you a real professional agent-based modeling. So the model that we did is completely in agent-based, and you can then extend and customize as you want. We did many customization, and at this time for this project, we embedded a prognostic health model, so a machine learning model to estimate the life of the component, and then you can integrate also everything with the enterprise application. So this is where the role of engineering sometimes will be placed. So what we model? We model the van. So as I said, we did a complete pure agent-based model. So we have the van. The van are flowing through the line. Each van is a different agent. They are characterized as of having different types. Different types of van consume require different utilization of the robots. So the degradation of the components is different because of the production mix. Then we have the working station. Working station takes the van and provide all the work necessary to carry out the production. And each working station is described to have a certain number of robots, and that vary from station to station. And at the end, we had the robots that we said already before was described for his prognostic health model. So the model that gives you the idea of how it will degrade over the time because of the signal that we are getting at that moment. This is an example of a prognostic model. So I'm not an expert, so please don't ask me to go into details of that. But you get the signal. So the line you see, you get a raw signal. You filter the signal. And on the filter signal, you try to put in place different regression models in order to predict the point in time when the component will break. And this is adaptive because you see with the GIF or with the GIF over there, that by collecting signal, by training this model, the slope of the line will change. Okay. And the signal that we measure were the resistance, the electrical resistance. So we had to find a rule, a remaining useful life graph in which we had the number of electrode changes in respect of the resistance, so the micro-ohm on the y-axis. So we had the possibility to exploit the data collected from IoT sensors, and we used the IoT sensor to feed an agent-based and PHM model. So the PHM model were put inside an agent that could create the virtual, I can say, the virtual experiment in order to give to manager the intelligence to take informed decisions. So we are not going to try to substitute the manager, but we just want to put all the stakeholders of the maintenance process on reasoning on a same base. So having a tool in the middle of the table to work together and to understand the best way to exploit the benefit of maintenance. So deciding where to invest and how to invest in a certain maintenance policy in respect of another. So and all these were put into a change management project that could be exploited in the future. So I have just a short video in order to better show you what we created. Wow, it worked. So this is the interface of the model where you can choose different, for each robot you can choose different maintenance policy. So you can decide to go to a certain policy for a robot in respect of another. You can change all the parameters related to maintenance, to the settings of mean time between failure or mean time to repair, different characteristics of the line. So these were the operation line, where you have the robots, number of shunt spares, number of points per van. And then you simulate and you get your dashboard in which you have your total production, the maintenance time, the accumulated maintenance time, and the total cost for spare part and for cost for working hour of the maintenance. And then one important thing that we provided was a scenario comparison in which you could put together different scenarios in order to understand which provide you the best benefits. I think that this was one of the most important features that we put in the model, because it could give in a very short, in a very easy way, the idea of how a certain change, a certain level, could impact on the maintenance cost. So I think that you can skip. Oops, it's mine. So benefits. On a customer's perspective, I think even if a real quantitative return is not still possible to achieve, because the limitation of the project that we put in place, so we are just modeling one of the most critical component, but not all the critical components of the line. So we cannot understand the benefit of a systemic model in this sense. We can already say that the ROI or the economical benefits of advanced maintenance techniques should be carefully evaluated before the implementation, because sometimes it happens that the trade-off between cost of implementation and benefits sometimes is much higher on simpler maintenance policy. Like, for instance, if you have spare capacity, if your spare part doesn't cost too much, if the availability of the spare part is easy, sometimes just I can say just a condition-based maintenance could be enough. So again, maintenance 4.0 is a very good topic, but in our opinion should be really well evaluated before the implementation. And from our perspective, we just had the occasion to explore more in depth the connection between and the integration between AnyLogic, so simulation, and machine learning techniques. We touched this in the past with other projects like clinical research in Pfizer, but we are now understanding that it's a key of connecting two very powerful data analytics technique, and this could be a good point for future project. So we did something, but it's not enough for sure. So the first step will be to conclude what we did with our prototypes. So to model the entire line, to exploit, to get the signal from not only from the shunt but from other components, in order to evaluate the real benefit of implementing some algorithms in respect of a simpler maintenance policy. And we need also to create a certain stochastic model in order to not only a what-if analysis like the one that we did, quite deterministic, but taking into account the stochasticity you could have in the failure. We will need to implement a Monte Carlo model in order to really understand the return on investment. Another point that we discover, I was talking before about cost deployment and the importance that cost deployment has in world-class manufacturing. So the idea is that instead of using the model only for, I can say, test ex ante possible scenarios, possible maintenance policy in order to understand the impact of the change, you could also use the model ex post on some events already occurred in order to to apply the real cost to the root cause of a certain event. So, for instance, when you have a failure, when your plant stops, you are the stop of a certain workstation propagate all over the line and maybe all over the plant, because you have in lean manufacturing you have very short buffers. So if the event is critical and is big, it's possible to stop the entire plant. So understanding the real cause of this event is another way to highlight the importance of this component and the importance of intervention on solving this possible issue that could happen also in the future. And at least we should implement again what I said before related to the change management. So maintenance control tower could be a tool that could support the discussion and the awareness about an entire process, organization process for improving the maintenance. I think that I finished there.
Hi, so you said that you were using sensor data to try and predict remaining useful life of components. What sort of baseline do you have for saying this signal means that a component is broken? Or is it just comparing the signals to one another and finding which one is weakest?
Okay, so we had different, we had different trajectories, so we had different failed component. So in our track history, we had a different failed component. So we know the threshold, we know when a component failed. So this is, and we train the model, we train the algorithm with this data in order to get the remaining useful life. Thank you.